Welcome to the Is It Observable YouTube channel. So if you're connected live, it means that you're interested to this live stream event, the Observable Lightning Talks. So if you have never had a chance to connect to the Is It Observable Lightning Talks, you will see that it's great live 1 hour, 10 minutes live stream where we'll have guests that will share topics, methodology around SRE, Kubernetes, and of course, Observability in general or OpenTelemetry. And today, we're going to mainly focus on Observability. You see, there's a lot of great topics covered. So I'm very excited about today's Observable Lightning Talk. So as a flow, just to remind, so we will have today 3 Lightning Talks again. Every Lightning Talks will be have 15 will be 15 minutes in total, maximum. We don't take questions during the talk. That's why we end up with a panel discussion at the end of this live stream. So if you have any questions you want to ask to the speaker, note them down, because at the panel discussion we'll take at least 15 minutes to talk, exchange about each individual talk that has been presented. And for today, for the first Observable Lightning Talks, in fact, of 24, sorry, I'll lose, I'll keep track. I'm already in the future. We have 3 awesome guests. So we have Braydon Kains. So I had the honor to meet Braydon Kains in KubeCon Chicago, and you'll see he knows a lot about agent, and he's going to talk about how to find bottlenecks in your agents. Follow up that we'll have Natan, Yellin from Robusta, and it's going to be a very interesting talk track because a lot of people talk about AI, machine learning, and I think it will be very interesting, specifically in the context of observability. So a practical guide to building automated alert investigations pipeline using LLMs. And last, we have a well-known evangelist. So he owns his own YouTube channel called the Observability Talks. Awesome channel. I will recommend to watch it. It's Dotan Horovits. So I'm very excited to have Dotan today, and he will share the latest news with the OpenTelemetry project. So without waiting more, I would like to start with the first speaker, which is Braydon, and which have. Hey, Braydon, how are you?
Good. How are you?
I'm very good, very good. So you're working at Google, and
yes, that's right.
And I know that you're contributing a lot in the agent space. So FriendBit and also OpenTelemetry Collector.
Yeah.
Yeah, a lot of and also I think you have your own open source project that is very popular. So could you just present it quickly?
Yeah. So I also work on a tool called YAML, I guess is how you'd say it out loud. I don't say it out loud a whole lot. But it is a sort of traditional text formatting tool designed for YAML. I made it back when I was supposed to integrate that into our team's repos, but all of the YAML formatters that I could find required Node or Python to be installed, and I didn't want to force my team to install it. So I figured, how hard could it be? Which is, famous first words. I did end up getting something together, and then it took off like I didn't expect. So clearly some other people had the same problem that I did, and it's been a lot of fun to work on it.
Yeah, so thanks for providing this to the community. And so I'll leave you on stage. You have 15 minutes to present, and I'm very excited to hear how to find bottlenecks in our agents. So see you in 15 minutes.
Sounds great. All right. I'm going to start a timer here. I'm going to try and keep this efficient, just like the agents. So this talk is called Learning to Fly, and it's how to find bottlenecks in your observability agents. Luckily,
Braydon, I don't hear you anymore. I don't know if it's normal.
I got muted. I don't know how that happened. I think I pressed spacebar while I was focused on the wrong window.
All right. So let you continue.
Yeah. So let's start that over. This is the title of the talk. That's all I was saying. You didn't miss a whole lot. Enrique already did the introduction for me, so I don't need to go too much into it. But I work at Google Cloud. Primarily, the team I'm on works on a product called the Ops Agent. So if you're a Google Cloud user, you might be familiar with that. But mostly my job is to contribute to the open source projects that make the ops agent work. So I spend a lot of time, you'll see me around FluentBit, the OpenTelemetry collector, other OpenTelemetry repos like the semantic conventions. And in terms of work that I do that's private, that probably won't stay private, is I've been doing a lot of performance analysis and benchmarking. And that's sort of feeding into what this talk is about. I'm going to be presenting this talk basically as a demo, kind of. I'm not using any Google-specific technology in this. The source for the demo will be available at the end. I'll have Enrique show a link. But so you can run this demo yourself afterwards. But using the OpenTelemetry collector, I'm going to look at a somewhat naive metrics pipeline and talk about the different spots that we can shrink it down to make it more efficient. So the scenario here is that we are scraping some Prometheus endpoints, and we're going to be sending them to an OTLP destination. We're going to be scraping the node exporter, which is a really popular Prometheus exporter that most people who are familiar with Prometheus are also familiar with. We're also going to be scraping the OTel self metrics. And finally, we're going to be scraping an endpoint that is definitely not Avalanche, the Prometheus load generator. Shout outs to them, by the way. The requests also need to be batched. A lot of common metrics backends that aren't something like a raw self-hosted Prometheus. They may have limits on how many time series or how many pieces of data can be in one request. So we're also batching them to make sure that we don't exceed that. That's an arbitrary limit, and you'll see why. So the demo here is inside a Docker container. I'm going to be running, what am I doing first? So I'm going to be running a OpenTelemetry collector. It's going to be scraping its own host metrics just so I can track the stats of it. It's going to be scraping these Prometheus endpoints. We are batching the processes to the max that our endpoint, I'm pretending that our endpoint can accept. And we're going to be exporting it to a server. It's just a small like pretend server that I wrote that has like a random response time to sort of simulate the network requests taking different amounts of time, like an indeterminate amount of time to finish. In this first scenario, it's not literally running right now. And the reason for that is that my giant host machine can't even run the thing at the same time as anything else. So the memory usage for the first scenario, which was to run the OTel collector on, it's approximately 1 million metrics, a little bit more than that when you consider node exporter and OTel self metrics at the same time. And the memory usage results were pretty heavy. For math's sake, 10,000 megabytes is 10 gigabytes. So we're hovering in and around the 8 or 9 gigabyte average memory usage. It is quite a lot of metrics. 1 million metrics, maybe for a Prometheus instance, scraping a bunch of different spots, that's not a lot. But when you're running an agent, usually agent means running alongside something else, like you're running on a VM or you're running something in your cluster and you want that agent to not be massive. 9 gigabytes is pretty intense. One of the reasons that this is so big, for the most part, it's because there's so many metrics, and we'll get into that more later. But the biggest reason that we are going so high is actually that batching requirement that we put on. When the receiver gets a whole batch of data and it's too big, 1 million metrics is too many for our limit, the batch processor will start to split them into multiple batches and queue them up for sending out to the exporter. When we have so many metrics at once that are being split up into so many batches and only one exporter constantly churning through them, eventually the agent just has to persist all of these over time. And it can start to get backed up. And there's multiple strategies around this. If you can try to send larger batches to reduce this problem. If you're in FluentBit land, for example, this similar sort of setup can happen in FluentBit. But in FluentBit, the exporter has a way, some exporters, most common exporters, have ways to turn them into like a thread pool of workers. So for example, instead of one exporter sending stuff, you could have like 8 threads all running in the batch. The batches can be flushed to each of them in sort of a round robin fashion. And that's a good way to get around this when you're in FluentBit, if you really need to send all this data. But the strategy that we're going to take, since we're in OpenTelemetry collector, and we really don't want to start losing data by applying back pressure, we're going to try and reduce the amount of metrics that we're sending. So the second scenario here, in the second scenario, we're going to take our largest endpoint, and we're going to be applying a relabel config that only keeps one series out of a set. So like we want to, basically we're trying to reduce the amount of points that we're actually going to send out. We're still scraping everything, but we're going to send less points to the output. And so if we look at the memory usage of this, we're quite a bit lower. We're definitely not peaking as much as we were before. And we're sort of averaging more of a 3 or 4 gigabyte sort of amount. This is much more manageable, but it's still pretty high. You know, we're only sending under the hood. You'll see if you look at the demo source code, this is only sending 1/10 of the points that we're sending here. But yet the memory usage is still so high. So what's the next step? The next thing to talk about would be how Prometheus scraping works in general. The Prometheus scraper receiver in the OpenTelemetry collector, it uses the same library under the hood as a full Prometheus instance would for scraping. It's the same process. And how the Prometheus scraper works is it slurps up the entire scrape, all of the metrics that are in the scrape, then applies relabeling to them, and then sends it along to the rest of the pipeline. So in our current setup, we're applying relabeling and sending less metrics down the line, but the Prometheus scraper, the receiver, still needs to slurp in the entire scrape into memory. That's very memory intensive. Some Prometheus exporters will provide ways for you to reduce the number of metrics that are actually being sent. Like you can disable, in the node exporter, you can disable different collectors that have high cardinality, or in some database exporters, you can change stuff as well. So we're going to try that next. We're going to try reducing the number of points that the exporter is sending. In this third scenario, we're going to, let's see, scenarios. This is the, right? Yeah. Wrong. We're going to send only 50,000 metrics. So we've gone down quite a bit. We're going from sending 1 million to sending 50,000. Chances are, in a real scenario, you probably can't reduce it quite that much. But I did it this drastically to show the effect of reducing the size of your scrapes. With this setup, we're down below 1 gigabyte, which is good. Because we're actually scraping and retaining in memory so much fewer metrics than before. It means we don't need quite as much memory, which is good. So now the receiver part, the processor part, and the exporter part all have a lot less work to do than when in the original setup. But with 5 minutes left, there's still one more thing we can do to make this even better. And in the next section, this is probably the deepest technical part. Don't worry if this explanation doesn't make sense. I also might not be explaining it the best. When a binary gets loaded into memory, in Linux at least, you can actually look at all of the memory mappings using this command, pmap. Oops, wrong container. So using this, we can actually get a breakdown of what parts of the binary are taking the most memory. The biggest one for us, obviously, is this mapping here. This is where Go starts allocating heap memory. And generally, anything that starts with a C or around it is where Go starts allocating heap memory and decides when to make a new mapping for new memory arenas. That gets pretty deep. But anyways, that's the largest segment for us. But there are two other very large segments which are here and here. These mappings are named with the name of the binary, which is how we know that this is data that's actually coming from the binary. And you can actually see here X for executable, meaning that this is the text segment of the binary. You can also tell because anyone who knows how ELF, executable Linux format binaries work, knows that the entry point for the binary is usually here. And this is where the data from the binary, so any sort of constants known at compile time, and in Go specifically, there's a big one called the Go program counter line table, which is how, if you're familiar with panic in Go, you can get back traces even when you have like a stripped production binary. And the reason is that the stripped binary still contains the Go program counter line tab. So in the assembly instructions of the program, it's still maintaining a mapping for this line, like this Go function at this line maps to this instruction. So if there's a panic or something at that instruction, it can generate the backtrace that way with that information. You actually cannot strip that out of Go binaries, even when you strip all other symbols to make it as small as possible. So yeah, this drawing just says the .text segment of the ELF binary, which is the assembly instructions, the executable code, gets mapped into this segment, and these two get mapped into this segment. The reason I'm saying all this is because for all of this, I have been using OTelCall contrib, which is a release of OpenTelemetry collector that has every official OpenTelemetry plugin possible. Now you might be using a distribution from your chosen provider if that's available, but I can imagine that there are probably some people who started at contrib and just like decided to try it out, wanted to see what they could set up. The problem with contrib is that it has everything. Every single thing in the OpenTelemetry collector contrib repo and the core OpenTelemetry collector repo is all there, all statically linked into the binary when Go builds it. The statically linked Go binaries are very useful and convenient, but the problem is that these segments get gigantic when you have so many dependencies and so much code that needs to be run. So what can you do instead? There was a talk at the last, I believe it was the last set of observability talks about building your own collector. There is a tool called the OpenTelemetry Collector Builder that will allow you to only specify only specify the plugins that you want to be present. And that's really useful because that means you can have a smaller binary in the end. If you look at the size of, if you look at the size of this, that's 232 megabytes. That's the actual released binary from the OpenTelemetry project. If we use this other one I built, I called it OTel Small instead of OTelCall. It's only 86 megabytes because it only contains the plugins that we need for our run. And if we graph the memory usage of this one that's running, we get down to an average of about 350, 400 megabytes, which is a little bit low, around the same amount lower as our previous scenario. So, you know, we save a good 80, 90 megabytes just by building our own OTel collector instead of using contrib. And that is everything I have for you. I think I'm just in time according to my own clock. So hopefully that was useful to you. It's possible that maybe you can't directly apply these exact strategies to your scenario, but the goal of the talk was to show you what sort of strategies you can use when you're trying to look into how the agents work and how to make your own pipelines work better. So.
Awesome. Just in time. Wow. That is timing perfect. And you mentioned something very interesting, and I will ask those questions later on. Again, if you had also questions to Braydon, keep those questions somewhere. We will ask them during the panel discussion. So let's move on with the next speaker. And thanks, Braydon, and see you in a few minutes for the panel discussion. Wow, I think I had a click issue because I launched several times the jingle. So I don't know. Sorry for that. Hi, Natan. How are you?
Doing good. That was a cool talk by Braydon, especially the part about alpha optimization at the end.
Yeah, and I was surprised on a few numbers, but again, I will definitely ask those questions later on, because I'm doing a benchmark on the collector. So this was very interesting for me at the end. So if you never heard about Natan, so Natan is the owner of the company called Robusta. If you never heard of Robusta, check it out on LinkedIn. He does amazing things in the community space. He always have great ideas. Every time I meet him in conferences, he also usually is pushing very hard on the fact that you should not put limits on CPU, but that's another debate for today. So I'm really excited to get Natan today, and the topic that you picked is really, really interesting. So I'm very excited to learn more about it, because it's a very trendy topic. So without any more, I will let you 50 minutes and we will talk later on.
All right. Thank you very much. So I'll be talking today about using AI to find the root cause of alerts. And of course, unless you've been living under a rock, then everyone knows about ChatGPT. And ChatGPT under the hood is powered by a technology called LLMs, or large language models. And we're going to talk today about how you can really use that type of technology in AI to find the root cause of alerts. First, let me just give some really brief background about myself. So I'm the CEO of a startup called Robusta Dev, and we do root cause analysis of cloud alerts, especially on Kubernetes. And I'm usually at KubeCon with the team, and we're at the Robusta booth, and we usually are the guys with the big giant helm. So if anyone's at KubeCon, please come by and say hello. Now, I want to just start with a little bit of motivation. So I used to be a software developer for many years, and at many of those jobs, I had a Slack channel that had alerts coming in from the cloud, from whatever monitoring or observability solution we were using. The last job, it was Prometheus, and we would get a whole lot of alerts here. Here, there's 87 new alerts, new messages since I last looked. And those alerts could represent a real issue that is costing my company revenue. Production is down, people are angry. If I have an online shopping site and customers aren't purchasing while the site is down, they're going elsewhere. So this could be a real issue that's costing us money, or this could just be a false alarm. Could just be an alert that isn't tuned properly, and could be a real alert, but it doesn't have a big impact. And the key challenge is to figure out, okay, well, given an alert that came in, does this need my attention now? If I got pinged in the middle of the night, is this a real problem? What's the impact? And of course, how can we go and fix that as fast as possible if it is a real alert? So that's what we're going to be applying AI to. We're going to be applying AI to that specific problem, and we're going to be doing so iteratively. So we're going to start with like a really dumb solution, and we'll get very rapidly to something that's actually really interesting and useful. But we're going to do this iteratively, and each time we're going to show a solution, we're going to show the challenges and problems with that solution, and then we're going to show a new solution that replaces that. So let's just start with a naive approach. I take an alert from over here about an issue, and the examples I'm giving here are about Kubernetes, but this is broadly applicable. I take an alert and I copy paste the metadata for that alert, and I put it into ChatGPT and I ask ChatGPT, why did it fire? Right? So this is kind of dumb, but we'll be able to use this afterwards to contrast it with other approaches that work well. So I put in, why did this alert fire and how should I troubleshoot it? Be concise. And I put in here details on the alert that is firing. And what I get back from ChatGPT is, okay, this alert fired because the pod has been in non-ready status for more than 15 minutes, and some of the pods are unhealthy. This is really generic advice. This doesn't help me a lot. And I don't get any really good insights out of this. This doesn't get me closer in the middle of the night to understanding why this alert is firing and what I should do about it. And the question is why? Well, if we go back to this for a second, and like imagine I called you up and you were on call and I asked you in the middle of the night, I said, why is this alert firing? And you're a great DevOps engineer and you really know Kubernetes. You wouldn't know either, because there actually isn't enough data in here to be able to tell. We're missing information, so a human couldn't do it either. So it's not a fundamental limitation of AI. It's garbage in, garbage out. I'm asking it to tell me why something is firing when it doesn't have enough context to actually figure out why. So what we're going to look at is we're going to upgrade the solution out to solution number 2, and we're going to use a technique that's called RAG, or Retrieval Augmented Generation. And essentially what this says is we're going to take an alert and we're going to feed into the AI, into the LLM, not just that alert, but we're going to feed in extra information that we retrieve from different sources. I put here the definition that NVIDIA gives. a technique for enhancing the accuracy and reliability of generative AI models with facts fetched from external sources. So conceptually, what we're doing is we're taking an alert, we're gathering up external information like logs about this application, like events from the cluster. We're gathering up all this information and we're shipping them in together to the LLM. So now we're asking the LLM, okay, why did this occur? Here's the alert, and here's all this extra information you can use to troubleshoot it. And here's an example that we built into our product. And we have an AI Analyze Problems button here. And when you click that, we essentially suck up all the data on this page and other data. We look at recent changes you made to your application. We look at pod logs. We look at Kubernetes events. We look at all this data, and we feed that all in. And now we see if we can get back an analysis for why an alert occurred. So let me show you the results on this. And we get fairly accurate results. Here's an example based on the information, provided information, again, relying on the information we fed in. The main problem preventing that from running correctly is that the pod is unschedulable due to node affinity selectors not matching any nodes. And what's really cool about this approach with RAG is we can actually cite our sources. So we can say, like this is indicated by the following quote from Kubernetes events, and we can show not just the conclusion from the AI, but we can show what sources the AI relied on to reach that conclusion. And if you've used a recent version of ChatGPT, you can actually see something like this. Sometimes you will ask a question, and it will go and it will search the internet, and it will show you which pages it searched. So it's a very similar approach. And what's really cool is we're getting the result, and then you don't have to just take the AI's word for it, right? When it comes to reliability, you can see what it relied on to reach that conclusion, and you can kind of tell yourself. And then essentially, the AI is going and picking out useful information, and drawing your attention to the areas that you should be looking at. So overall, this approach with RAG gives some pretty decent results. And it's also something that's fairly easy to build yourself. If you're building something like this yourself, what essentially you're doing is you have an alert, you have an incident that occurs. You want to take that and then do like a search on other data sources. Like if you have an alert that occurs on a pod, fetch the pod logs. If you have an alert that occurs on a node, fetch the data on the node, right? So gather this information, and there are more complex techniques as well, like vector databases and all sorts of other techniques for figuring out what you want to fetch. And then you feed all that information into the LLM together, do an API call to OpenAI, and again, you get back pretty decent results. So this is pretty good, but there's two problems with this. The first problem is we as a human are actually deciding what sources are relevant, right? So when we're looking at an issue on a pod, we're saying what will be relevant is to look at the pod logs, and what will be relevant is to look at like the Kubernetes events, or to look at some other things. We kind of have a non-AI, like a predefined decision we made as a human that the most relevant information for these alerts will be X, Y, and Z. And then we gather up X, Y, and Z, we feed it in, and then we get back to analysis. Well, sometimes the information you need isn't in X, Y, and Z. So if we're giving a human analogy for this, right? Like the first approach that we had is I call you up on the phone and I say, here's an alert, why did it fire? And you say, well, I don't know, I don't have enough information. The second approach with RAG is saying, calling you up on the phone and saying, here's an alert, here's why it fired, here are the pod logs, here's some other information, tell me why this fired. And you say, well, actually, the information you just provided me isn't so relevant, and then you're stuck. And finally, a final limitation of this is what's called a context window. If you've used ChatGPT, then you may know that when you type a lot of stuff into ChatGPT, you get an error. You can't put in more than approximately around 15,000 characters, what's called the token limit on the context window. So you can't put in too much information because the way these models are built, they don't know how to handle too much information at once. So we actually have a problem. On the one hand, we want to feed in all the information in the world, so that includes at least some relevant information. On the other hand, we can't feed in all the information in the world because we're limited to, let's say, 15,000 characters, right? So there are some challenges around that. So I'm going to show now a third approach. And before that, I want to just show the key insight. When a human is troubleshooting an alert, they do not go and run like a set of commands up front and gather information and then go and troubleshoot. When a human investigates an alert, it's an iterative process. So you look at one thing, kind of think, then you say, okay, actually I should look over there. Then you go and you look at something else. Then you think, you say, okay, well, you build a picture in your head. What have I seen so far? What do I know? What do I not know? You do another iteration, you gather more data. And you have this iterative process where you're going and each time you're gathering more data, but you're only gathering the bits of data that are relevant. So you might actually gather very little data, but each bit of data you gather, you have a reason for gathering. So that's trying to apply this approach now to AI investigation of alerts. So what we're going to have is we're going to have an agent, and we have some cloud environment or observability solution or monitoring data. And essentially the agent can work in iterations where it fetches data on demand from the cloud environment. That goes back to the agent. The agent thinks, and then the agent decides, well, do I have enough information to output a reliable analysis, or am I still missing information? And if I'm missing information, I go back and I do this iteration again. So the key insight here is we're like teaching an AI how to troubleshoot the way a human troubleshoots. This is like me calling you up on the phone and saying, why this alert fine? You say, okay, well, to know that, please run this command and give me the output. Okay, I do that. I say, do you have enough information yet? You say, no, actually run this command. Give me this information. Can you now go into this system and look at this graph and tell me what you see there? And when you have that kind of iterative process, then like a human who's good and knows what they're doing can actually go and troubleshoot really well. And that's what we're going to apply here. And I want to show you some results of that. So I'm actually taking the very first result, the very first example I showed you, where we took that alert and we fed it in, we said, why was it firing? It gave me a very generic answer. I've done the same thing here. And we have a pod running on Kubernetes. Again, my examples are Kubernetes specific, but the technique is really general. And saying you have an invalid image name. So you're trying to run an application with a Docker image that doesn't exist. And none of that was in the alert itself. None of that was even like data that we told it to go and gather. It figured out on its own what it has to look at. And it was able to gather that data and to use that data to then figure out what occurred. So we get very, very accurate results with this approach. And it's actually really easy to extend beyond Kubernetes, right? Because you don't need to do all this work now that you have to do with RAG and retrieval augmented generation, where you're figuring out in advance like what data you're going to augment. So this is a really good and like generalizable approach. And it's also really easy to integrate with organizational data, right? Like a human might go and look in the Slack channel at previous cases where an incident occurred. Well, why can't an autonomous agent do the same thing? Now, I want to just show a few more results. So here's an example where we pointed at an alert that said there's a problem with this deployment on Kubernetes, and it figured out that in this deployment, there's an issue with the quota. So in Kubernetes, you can have these quotas that define the maximum amount of resources you can allocate. And it looked at that and figured out that you're exceeding the quota, and that's why this issue is occurring. Here's a different example where we actually fed in an alert that's on a pod. It was able to go and figure out, no, this issue didn't just have to do with that pod. It actually is related to a problem that was going on at the node. So it's kind of an iterative approach where you're looking at the pod, this Kubernetes application, and then it turns out the problem isn't on the application, it's on the virtual machine it's running on, right? The node. So it's able to do that iteration and like jump from one object to the related object to the related object. That's really cool. And what's cool about these is we never trained on these. We never tested with them. Even these came up like when we put it on real world data, and then suddenly we saw these results. So that's really cool. Finally, we started to see a little bit of emergent behavior and it doing things that we had never taught it to do and we didn't expect it to do. So as an example here, we had an issue here with a certain volume, like a disk on Kubernetes, a PVC it's called. And we suddenly got back results that were telling us not just what was going on with that volume, but we're saying two pods, these two applications are using this volume. And we started getting back these results, seeing other things, telling us like which application was accessing that data. And that was very surprising for us because we never taught it to do that. We never told it to do that. We never, like it was reaching an insight here that we actually didn't even know ourselves as humans how to reach. So we had done like that retrieval augmented generation approach, then it never would have seen this because we didn't even know where to feed this data in from, but it was able to figure out on its own. So that was a really cool result that we saw. Finally, I want to just say a word about like the future work and directions that we're looking at and what we think the future holds, which is figuring out how to do remediations. So as an example here, we took care of an application on Kubernetes, and this application has actually used up too much memory. So it's run out of memory. And what we've then asked it to do is we fed this into like a little command line that we're building, maybe a big command line already, but we fed this into a tool. We said, okay, given this application, it ran out of resources. Well, how do I go and how do I fix that problem? And being able to get back a result that says, okay, actually run this command to fix the problem. And this is very non-trivial because like you have to figure out even where to go and like where that thing is coming from. And on Kubernetes, things can come from many places and like which configuration value. It's actually really a very hard and annoying problem if you think about it. And this is an area that we're also looking at. And this is an area that seems very, very tractable for LLMs, for large language models, being able to go and using the model itself, using the LLM with the right context to figure out where you can actually go and edit the code to fix this problem, and even being able to go and open a PR on GitHub. And if you think about this, the way you do this is really just like what we said before, either using that RAG approach or using an agent-driven approach where we can kind of explore your code on GitHub on its own and then find the right place to modify. So that's it. And I think we're just on time. But thank you very much.
You were also very respecting your time. So
you're on mute, Henrik.
I am on mute. No, you hear me? Hello?
Yeah, I hear you now. Yeah.
Okay. No, a very interesting topic. I have a lot of questions, to be honest, and I will keep them for later. So thanks for presenting it. It's very interesting and very promising, to be honest. I really like the topics. So thanks, and see you in a few minutes for the panel discussion then. Hi, Dotan. How are you?
I'm fine. How are you, Henrik?
I'm very good. Very good. Very excited to have you here for the live stream. So for those who never heard about Dotan, so first of all, check it out. He's speaking in many conferences. He runs the Open Observability Talks, like I mentioned. I will share the links in a few minutes. So check it out. He usually gets a guest interview, talking about topics about the Open Observability world. So very interesting to listen to that. And Dotan is the Chief Technology Evangelist at logs.io. So yeah, very happy to have you here at the Observable Lightning Talks. And yeah, I will let you 15 minutes to talk about what's new in the OpenTelemetry project. See you in a few minutes.
Amazing. Thank you. Thank you very much. Yeah, and now we can see the screen. And as mentioned, let's talk about what's new in OpenTelemetry. Obviously, you folks following this show, you know about OpenTelemetry. Just a quick word about myself. As mentioned, I work for logs.io, maybe another capacity that Henrik didn't mention. I'm also a Cloud Native Computing Foundation ambassador, CNCF ambassador. So if you have anything related to the CNCF ecosystem, also feel free to reach out to me, basically on any channel, Horovits, my surname, as you can see. So Mastodon, Twitter, LinkedIn, Medium, whatnot. And you're all welcome, obviously, to also, if you like videocasts and podcasts and shows like that, my show Open Observability Talks about open source DevOps, observability and the likes. More than happy to see you there as well. And let's go straight to OpenTelemetry. You probably already know, but just very briefly, a framework for generating and collecting telemetry data across all the observability pillars, primarily traces, metrics, and logs. So one framework to rule them all, if you like. It's an incubating project under the CNCF, the Cloud Native Computing Foundation. It actually started as a merge of Open Tracing and Open Census. It's been accepted as a CNCF sandbox back in 2019, and then into the CNCF incubation in 2021. And with that, let's jump straight to what's new in the project's adoption and activity. And I'm very happy and proud to say that we are today, or OpenTelemetry today, is the second most active CNCF project behind Kubernetes itself. So very impressive. And this is, by the way, taken from the CNCF dev stats. It's a public link, open Grafana style dashboard that you can examine yourselves. So that's from the last 30 days. But if we see the activity in the numbers, diving into that, you can see how it got to be so active: 55,000, almost 56,000 code commits, 67,000 pull requests, 466K contributions. And the most important thing for me, as you can see, over 9,100 individuals contributing code, and over 1,100 companies contributing code. So that's amazing. By the way, this is taken from a report we published at the CNCF, a project journey report for OpenTelemetry, looking back at all the time since it started back in 2019. And Also amazing to see the growth in contributors over the years, which has only actually accelerated in the past year and a half, if you can see the slope there, leading to, as I mentioned, over 9,100 individuals, probably by now closer to 10,000. And also very impressive to see how the numbers of contributing companies has risen every quarter in an impressive rate, with today's over 1,100 companies. And also in the mix, you see all the cloud vendors are there. Amazon, Google, Microsoft are there. The monitoring and observability providers are there. And you can see obviously also the largest tech companies involved, also end users such as Facebook, Shopify, and Uber, and obviously also smaller players. So really a healthy mix and diversity in the project contributors. If you know open source, you know what to look for, and this is good signals. So that was about, very briefly, about the project adoption and activity. And now I'd like to very quickly go over the main components to level set the knowledge. Again, I assume that many of you already heard that, but just very briefly, so that we can then talk about the technical updates in the project. So OpenTelemetry provides, firstly, a unified set of vendor-agnostic APIs, SDKs, and tools for generating telemetry data from our applications. That's the bluish part on the left-hand side. So APIs, SDKs, auto-instrumentation agents in many programming languages, Java, Go, .NET, Python, and many more. Actually, this month's episode on Open Observability Talks, I'll discuss .NET and its native support for OpenTelemetry in the upcoming .NET 8 release. So if you're .NET developers, do check it out. It's going to be an interesting discussion. So that's one part, the instrumentation of our application. Then OpenTelemetry offers a standard way for collecting the telemetry data with OpenTelemetry Collector that we heard also in the first lightning talk today. This is the green part in the middle, and also a standard way for transmitting and exporting the telemetry. That's the OTLP protocol, the orange part that you can see on the graph there, on the diagram. And then exporting to whichever backend analysis tool you choose. So OpenTelemetry does not take any stand in the backend, and whichever backend you use, you probably find the relevant exporters. And you have a very rich suite of exporters in many protocols available already within OTel and within the contrib library within OTel Collector. You also have a very rich suite of receivers to ingest from many sources, whether your application, as mentioned, the SDKs and the APIs, but also from third-party tools. So Kafka, Docker, Kubernetes, Apache, Nginx, all of these have their own receivers, so a large suite there, and many processors to do all sorts of, we saw some examples in the first talk. So batching, that's obviously, but also filtering and all sorts of other processing that you'd like to do on your telemetry data. So that's really much in a nutshell about the main OpenTelemetry components in a nutshell. And you have the QR code, by the way, on the corner there for a more comprehensive guide if you want to read more about the components. One important thing that I do want to say beyond the components is, very importantly, the OpenTelemetry specification. And many people as end users are less exposed to that directly, but it's very important because the specification describes the cross-language requirements and expectations for all the OTel implementations. So you have the API spec, the SDK spec, the data spec, semantic conventions, and so on. All of that part of the OpenTelemetry open specification. And this comes to across, obviously, traces, metrics, and logs. And we'll see soon that even more than that. And this comes to solve the pain of fragmentation and the silos and making it a comprehensive, holistic framework. So it's important to note the specification. And now that we know the components, let's go over the project updates. And the biggest update by far on this front is that OpenTelemetry logging piece has reached GA, general availability. We've announced its stability, as it's called in the CNCF maturity terms, in the recent KubeCon. And actually, this marks an even bigger milestone, because with that, all the 3 pillars of observability, now that I don't like this term, but many use it, the 3 pillars, logs, metrics, and traces, are now generally available, that are stable, and are ready for use in production, with all the necessary guarantees, such as long-term support, backward compatibility, dependency isolation, the things that you look for. So this has been the original charter for OTel, and finally accomplished. So let's go over the state of these signals, the 3 pillars, the original charter. First, traces. I'll go according to the order that it matured. So traces was the first and most mature signal to GA, to get stable. Obviously, the API, SDK, protocol specifications are stable. The collector is stable. And also, it has the largest variety of client libraries that are stable, that are version 1.0 or above. Version 1.0, once the tracing implementation is complete. So, and as you can see here, Java, Go, .NET, C++, JavaScript, Python, PHP, Ruby, Swift, Erlang. A lot of work has been done on many of these. So very, very good. And maybe very importantly, stable, as I mentioned, means providing guarantees for long-term support, backward compatibility, dependency isolation, what you'd be seeking to run it in production environments. So that was tracing. Next up was metrics to reach GA, with obviously the APIs, SDKs, and the protocol reaching stability on the specification side. And already having implementations of the API and SDK specifications in Java, .NET, Python, JavaScript, stable. So, and more languages following. So very nice. The collector supports metric pipelines. And Prometheus support. We talked about about agent performance of Prometheus support in collaboration, by the way, with the Prometheus community. Which is part of the advantages of having both projects under the CNCF. So in the SDK, you have Prometheus exporters from the OTel SDK, and also in the OTel collector, you have Prometheus receivers and Prometheus remote write exporters, and also Prometheus to OTLP data model specification alignment, which was a very, very important activity that has been done between the two groups. So, and one node that is not actually, it's not on the OTel side, but on the Prometheus side, but very important noting as well, is that Prometheus also supports OTel. So it can ingest, actually also a recent update from the recent PromCon, and it can ingest OpenTelemetry metrics using a new OTLP compatible ingestion endpoint, and also other features. And actually, this is the OTel compatibility is going to be a major theme in Prometheus 3.0 that is coming out soon. So stay tuned on this one. And lastly, on the logging side, the recent one, as I mentioned, to join. The first focus was integration with existing logging systems. So we all have these flat files and unstructured logs. We needed to support them. The very basics is to fetch the logs and transmit over OTLP. And that is available with the SDK to allow the clients to ingest the logging data and then output the logs as part of the OTLP alongside traces and metrics. Lots of activity on log appenders in many languages. So log appenders provide an easy way to send logs via OTLP using existing logging libraries. And in addition, it can also automatically inject the trace context to be emitted with the log. So it's very good also to start doing the correlation. So if you use logging frameworks like in Java, Log4j, SLF4j, Logback, and all of that, it's very easy to migrate without changing your code just by a configuration of the appenders. So that's the first phase. The second phase was to build a new strongly typed and machine-readable logging format. And this is a lot of work that has been done on semantic conventions to support that piece. And that actually leads me to a major update. That Elastic Common Schema is merged into OTel semantic conventions for logs, so a major boost to both open source communities. Quickly, some more updates, adding continuous profiling, so going beyond the 3 pillars into supporting new telemetry data. There's a working group, a SIG created for that, and actually in late 23, as you can see here, the data model for profiling was released, along with prototype implementations for client libraries and the collector. It's quite influenced by pprof for those who know this one, and a major enhancement for OTel this year, 2024. And next update about RAM reuse and monitoring, definitely a lot of focus, client-side interactions. Obviously, you can do client-side with the existing JavaScript SDK, but you don't have the semantics for asking questions that are typical for client-side, like counting the number of new users versus returning users, or visualizing how users navigate the application UI, or identifying pages that generate high number of errors. All of these things require semantic conventions. This is the part, and if you are interested in that, follow up in the CNCF Slack, OTel client-side telemetry, lots of activity around that. Another area is to make more robust operation side for remote agent management. So obviously you already know about Kubernetes Operator from it's been already for over a year, and also advancements there like feature gate support and so on. But the other area of focus is OPAMP, Open Agent Management Protocol, that has been going on to define the specification, the protobuf schema, and implementation in Go already existing to support OPAMP. So that's on the ease of operation. Work on eBPF. You probably all hear this buzz about eBPF. So there's already Golang eBPF auto instrumentation agent. This is, by the way, from an episode I had on Open Observability Talks with Eden Federman, the creator of the eBPF Go auto instrumentation agent for OTel. And there are also activities. There's a SIG for that, and there's also more languages. So in general, lots of work on enhancing auto instrumentation and ease the onboarding of new users. Also, the demo, the OTel demo, community demo is now GA. If you're not familiar with that, with this demo, you can very quickly run a complete end-to-end distributed system instrumented with OTel. You have a mock-up astronomy shop that you can see on the right-hand side, and very elaborate architecture with many instrumented languages and third parties like Kafka and Redis and Postgres and so on. So a good example to use. We're reaching the end, so I know that there's a lot of that, but sunsetting open census. If you're still using open census or open tracing, time to move to OTel. It's been deprecated, it's been archived on GitHub, so good news, because you have already the parity, full parity from open census. So check it out. And if you, as I mentioned, if you want more information, you have the guide to OpenTelemetry, you have the QR code here or the short link. So check it out. Lots of more updates, just teasing you with a few of these. And with that, I will say thank you. I hope I am on time here, Hendrix.
Thanks. A lot of updates, and you covered everything. And I had a few questions about a few components, but I will give it to the end. Just a small teaser. So for those who just dropped the QR code, for those who wants to join the Open Observability Talks, here is the QR code, and also you can either watch it on YouTube, but also in different podcasting platform like Spotify. I think you're on another platform, no? Or just
many like Apple, Google, all the main podcast apps, or on YouTube, and we live stream on YouTube and Twitch and even X. So join us for the live streams if you want to also chime in with your questions and comments, or just this on demand as you like to listen on the podcast app.
Cool. All right, so let's jump into the panel discussions, so we can ask questions and get your questions from the audience. See you in a few minutes. All right. First of all, thank you for the three of you. So you did a great. You were respecting the timeline, so 50 minutes. That's a good. First of all, mission accomplished, and the topics were well covered. So again, I will start with my own questions, and I will probably ask Natan and Dotan and Braydon if you have questions to each of you. And of course, if anyone has questions from the talks that has been presented, drop your question in your your streaming platform. So it could be Facebook, YouTube, Twitch, or LinkedIn. But yeah, just drop it. So we'll start with Braydon. So first of all, I did a couple of a benchmark like you did with a lot of metrics, and yeah, and I discovered that the memory usage, like you were showing us, is usually coming from the metric perspective. Because metrics, as you explained, gather a lot of metrics, and then even if you put your label config, then you still have those metrics. So the job will be done at the collector level, at the receiver level. But what I did is I enabled the target allocator from the OpenTelemetry operator, and suddenly the resource usage were gone. So because it delegates back to the service allocator. So I was wondering if, because I was using Kubernetes SD configs to as a scrap config, and the target allocator used the HTTP SD config, so where the endpoint is reaching out an HTTP request to a target allocator that gives you, hey, here I have a list of jobs, here is your stuff, and scrap it. And I was wondering if the Kubernetes SD configs were somehow more heavy at the end compared to other configs. I don't know if you have done those type of comparisons or usage. You mentioned if I do you mentioned that you can filter the metrics in beforehand, so maybe with the URL. So could you give us more details on how we could reduce that to save some memory? For sure.
Yeah. So for the target allocator thing, I actually didn't really know what that was when you mentioned it, but I just went and looked. That makes sense. That being able to distribute it across like a fleet of collectors would be a big help. So that's probably, if you're in Kubernetes land, that's probably even better than what I had to say. I wasn't really looking at the Kubernetes scenario in the demo, but if you are in Kubernetes, that makes a lot of sense. Definitely do that if you're doing these sort of, gateway of collectors. So instead of running them as agents across the pod, you have one gateway and a bunch of collectors, and you can distribute stuff across it with the target allocator. That's a great pattern. If you know you're dealing with large metric volumes that you don't want to reduce, then that's a good way to do it. When you're talking about in agent mode, one of the reasons that this is so large is the scraping the entire scrape in at once. And when you look at the Prometheus library code, it's the same code as if an actual Prometheus instance was doing it. And typically in Prometheus land, it tends to be best practice to just like toss everything at Prometheus and let the Prometheus instance figure out what it does or doesn't want, or throw stuff away if it doesn't need it. So in that scenario, it doesn't really matter whether you're reducing how many metrics you're sending. But in this scenario where you have an agent, you want to collect stuff and send it somewhere else, like to an OTLP destination that can't scrape the Prometheus directly or something like that. That's a scenario where, and it does depend on your exporter, but if you can find ways on your exporter to export less metrics. And some people might not have the best feeling about doing that. Like they want to make sure all information is always being sent. But it's always important to look critically at the metrics that you're actually using and whether there's some that you can get rid of or not need.
And yeah, and I think the usually when I'm using the Prometheus receiver and the collector, I like to use relabel config because I can drop labels. I can reduce cardinality very easily from the relabel config. And it seems that if I'm doing this, I'm forcing to get the entire metric stack that you mentioned, and then I'm doing the filtering afterward. So I was really, if you have any materials that you can share, I can put down on the descriptions or on the show notes afterward. But how they could filter at the source. So I have an exporter. How can I reduce? Actually, let's say I have I have a Kepler. Kepler is a CNCF project that exposes the usage of your workload in Kubernetes, and they are a very high cardinality metric. So I was wondering if there's a way of basically at the source in Kepler saying just reduce that. I don't know how you do that. Do this, to be honest, but maybe you can give us a tips.
Yeah, I think so. Anton mentioned this in the chat, and that makes a lot of sense. Depending on the exporter, probably there will be ways to like allow or block certain metrics so that they aren't part of the export. So if whatever exporter you are using, it allows you to do that, and they all decide to implement this in different ways in my experience. But if they allow you to do that sort of thing, then that's probably where you want to look at. And I have when I was at KubeCon in Chicago just recently, there was a talk where someone was a Prometheus maintainer sort of had kind of a hot take about OpenTelemetry, this sort of pattern of the collector collecting stuff and remote writing it somewhere else. Specifically to Prometheus, he was talking about. He said that was kind of an anti-pattern because Prometheus should just be scraping this stuff. And I think that sort of leads to there's a lot of exporters who are only thinking about Prometheus. They just export everything, and like, who cares if you want to like disable or allow certain metrics. And so it does kind of depend. I've been thinking a little bit about like providing some sort of like filtering tool that you can like put in front of your Prometheus endpoint to like manually filter stuff out at that point, if there is an efficient way to do that that doesn't take that much resources compared to the OpenTelemetry collector scraping it. That's still very much in the like tossing around ideas phase though.
Okay, great. Thanks. Natan or Dotan, do you have any questions for Braydon?
I also wasn't familiar with the target allocator, so that was actually cool to learn about. I think Dotan might have, because this is Dotan's space.
I think that obviously we want to reduce the cardinality at the very least, or maybe toss metrics altogether. But practically working with tons of end users, the challenge usually is not in the technical way of do I do that to the exporter or in the ingestion or whatnot, rather than users actually not knowing to a large extent what they need, and then they result to the defaults. And the defaults, especially in the Kubernetes environment, are a bloat of metrics. And it's actually, I've looked at the increase in the amount of default metrics in Kubernetes over the years, and it's amazing how it's almost exponentially rising. So, and people still use the defaults, and that's the problem. People don't really have a good grasp of what they need for observability needs. What they don't start with the end in mind, and then derive, and they go the safe path as they feel it to go to the defaults, and that's what causes the bloat. So it goes for the entire metrics, or even the labels that many of which are never being put to use. So what we've been doing is working with people to actually help them even understand what they use or don't use. And if you even start by this element of observability of usage, you can get a lot of savings. So I find myself spending most of the time actually digging into what is being put to use. You find out that 70% are probably not used in any dashboard, any rule, or anything else. You start there with the low-hanging fruits, clean these, and you're already in a safer bet. So I'm saying usually the challenges that I find are not in a technical sense of how to drop and actually what to drop. That's my 2 cents.
Yeah, that's fully aligned with you. So usually we say, I want to be safe. I want to take everything, and we will see. We'll think about it later on. That's a good point. I agree.
But I don't go into the grocery and buy everything because I might need it for a recipe I'm going to do at home.
I've had trips like that.
Yeah, it's a bit like
that way. They do. But yeah, I remember once I was on a call with someone from AWS, and we were speaking about on the webinar, I think, and we were speaking about Prometheus, and he said, okay, yeah, the way you install Prometheus on an AWS cluster, an EKS cluster, is you install Prometheus and then you disable 80% what cAdvisor exports.
But from your talk perspective, Natan, you need to, in the case of using LLMs to investigate into your alerts, I guess you need details. Otherwise, if you start dropping relevant metrics, then your model won't work properly.
So a lot of the details are often redundant. I'll give you an example. I'll give you perhaps it's a stupid example, but I think it's illustrative. Like if you have a pod that crashes and you want to investigate why, or an application that's not responding, right? Like the traditional approach is, okay, well, we're going to gather all the logs. Of course, I'm going to ship all the logs from everything. Like that can be very big. Actually, you only need the logs that you would get with kubectl logs at that particular moment in time, right? You actually don't need logs from, like if you're doing the analysis in real time, you actually don't even need persistence on all the same amounts of data. So you can actually feed into your analysis like much more high cardinality data that's available in the moment. Whereas if you like ship all the data and then you do the analysis at query time, now you need vastly larger amounts of data because you have to have persisted everything. Like a different example of that is like if you're looking at why like there's an imageable backoff, right? That data is reflected across like probably dozens of metrics. It's reflected from the API server with kubectl. It's reflected in like different logs from kubelet. So like actually there's a lot of redundant data out there. So if it's actually an opportunity with LLMs to say like, here's the data that's available. Of the data that's available, what do I look at? Whereas if you're a human, like you're just looking at one side of data that you're used to, and different people have different things they're used to looking at. So then you actually need to sometimes collect a larger scope because people are querying it in different ways. So I think it's, from what we've seen, it would seem to suffer less from that problem. But I guess I'll finish with one extra thought here. There's something very curious about this that we didn't expect. LLMs turned out to in many ways be the opposite of everything we thought that AI would be. Meaning, like when we used to speak about AI 5 years ago, then we thought AI would be really good at logic and it would be really bad at creative things. Like that sounds like a weird statement now. Like it's even hard to remember this, like our state of mind. But it turns out that LLMs are really good at making stuff up. So they're really good at creative stuff, but they're really bad at science and like bar laws. We thought that LLMs would be able to like take this massive amount of data, just like machine learning algorithms do that aren't LLMs, and be able to make sense of that data. No, it turns out LLMs suffer from the same problems as humans. They can only look at a limited set of data. They also have context windows. Like they also have a set of data they can look at. So like in many ways, it's turned out that LLMs don't actually do as well with large, massive amounts of data because they're not, like they function more like a human than a machine in some sense. So the answer to your question is I don't know yet, but it seems like we're in the early innings of what root cause analysis with LLMs look like and like exactly how far we can get with that. But from the early results, it does seem you can actually get by with less data.
Yeah, but I think the OpenAI model is that more people utilizing and dropping content into OpenAI, more accurate will be the answer, because at the end you're feeding the model. So if I am, let's say, a military company, I may be very cautious about sending my data to OpenAI. So and we'll probably want to use like a private instance of any LLM and the technology, so then I can control exactly the type of information I'm sharing to the OpenAI, for example. So have you tested out to see if the algorithm would be as efficient if you were using with a private instance where you have to send the context, because at the end, probably the first hours it won't be so smart, but maybe after a few days, the end the model has enough data to be precise, or the logic, or I mean the answer will be more precise.
So everything we do is on private models. We mostly use Azure, and everything we do relies on each customer's data being segregated. So no cross-training between data. So like what one customer ships doesn't affect anything from another customer, because that's like a hard requirement in the enterprise. And there's like two ways you can work with LLMs. One approach is to like train them on a really big set of data that's kind of represents the domain. That's kind of what AI did, right? They trained on the whole internet, but then you can't get back reliable results with that. Like when you get back a result, it's based on the whole internet, and the whole internet has lots of lies. Right? So like, if you just train on data, like a lot of these problems you actually can't solve at training time. At training time, you can do like really good work in getting like results that are formatted a certain way. Like there are various things you can do, but a lot of it, like I spoke there about retrieval augmented generation, like actually by feeding in the sources and then teaching it to cite certain sources, you will get back better results, like more reliable results than if you train on those sources to begin with. So that's been our experience. So I think that a lot of the intelligence is actually more at like query. A lot of the intelligence is in how you feed data in, and not in how you train the model in advance. If that makes sense.
So now that are we going to rely on open AI or whatever LLM platforms to do our investigations, then we need to have significant observability layers on the on the LLM platform, because otherwise the investigation will be I don't know. We'll see. But I think, yeah, it means that all of us as a vendor, I mean, as an observability vendor or users, we have to put a lot of efforts to at least have enough observability from the LLM perspective.
Yeah, it's like a big thing now. There's like at least 100 startups, and all the major vendors are also like providing solutions just around observability into how the LLM is working. And it's a challenge. There's like a whole set of there's a whole set of companies that are going to be created just out of that. And I think a lot of value and revenue also for like the bigger vendors just out of getting visibility into like what exactly are these LLMs doing.
Sure, I agree. Dotan, do you have any questions for Natan, or Braydon, do you have any questions?
I have one. So Google Cloud has this service called error reporting, which allows like service teams to report when specific known types of errors are happening. And one of my teammates experimented with like taking an error reporting thing that the Google Cloud Ops agent reports, and seeing what the AI has to say about troubleshooting suggestions. And it basically just boiled down to like, hey, check the Ops agent docs. Like, thanks, I probably could have figured that out. What is a model like what you were talking about? That's like, it can gather context in like a project and context about your cluster and stuff like that. Is training that on like internal docs, like troubleshooting docs, playbooks, like documentation about your programs and stuff, would that have any effect on the output, or is it more important the context of what's actually happening in the project?
So what we've seen is you get good results when you actually make that part of the context. Meaning if you train on that, the problem is that LLMs don't know how to reliably cite data from their training sources. Meaning when you feed, like you train the LLM on the whole internet, it can't go back and say this data came from this URL I was trained on. Like it's kind of a mishmash, right? Like if you think of like you watch 100 movies, or if you watched 1,000 movies, and then like I show you a scene and say, what's the style on this? Like you might be able to tell me the style, but you might not be able to like say every one of the movies that like kind of influenced your thought on that. Or if you eat 100 restaurants, you say, I like this. Maybe you can sometimes say it reminds me of this dish at this restaurant, but you can't say everything that like kind of factored in your head into that. So there's like the taste of the LLM, so to speak, or the knowledge of the LLM is kind of like it loses the sources that it was trained on. But if you just train on those runbooks, then you have trained on those runbooks, that information will be embedded in the LLM. It will be hard for it to go into site package sources and say, because in this runbook it says X, Y, and Z. Whereas if you make that available as part of the context, and that's what you're feeding in with like RAG or with another method, then you actually get pretty good results where you can go back and you can cite the sources. So the way we're thinking about it, and like the best results that we're seeing, is not with train the LLM on all the docs, but rather give the LLM access, like as an autonomous agent, say you can troubleshoot, you can actually look at, like you're able to go and read these runbooks, and these are the runbooks that you can look at. So making it part of the context has given very promising results.
Interesting. Yeah, it makes sense.
Dotan, do you have any question for Natan?
No, I guess maybe one note to pay, especially for those working with OpenAI or other public services, is to be very cautious with doing the pre-processing and removing, obviously, all the sensitive data, something that some people had known public issues with that. So on the pre-processing and also on post-processing, make sure that you also validate the results. Sometimes they have some sort of a sentiment analysis that need to be taken place, because we've seen also AI taking some biases. So just reminding that this sounds good, the promise, but at least from our experience, and we've also experimented with getting some insights around alerting and things like that, to be all the training that you mentioned. So I won't repeat that, but also the pre and post processing, very, very important in these respects.
Yeah, if I could give people one tip, and I really hope no one from OpenAI is listening to this, don't use OpenAI, use Azure. Now, that's a little unfair to OpenAI, because if you use their API, they actually don't train on that. But like we consistently see that in the enterprise, people want to send stuff to Azure to private instances. Like that seems to be the way to go from like a security and from a regulatory perspective. And I really hope no one from OpenAI is listening to this. I think it may be more of a public image issue then it is actually a technical issue in terms of what they're doing with your data. But that does seem to be the trends.
Yeah, it's good. We're moving on to the next Terminator for sure in this approach. So Dotan, I have a few questions. So I didn't follow so much. You at the end you made some more updates slides. There were the profiling, OpenAMP, and other projects. And I don't know. I know that the specification was going on the right direction. Do you know where is it at as of now in terms of states? Do we expect to have any language that has the profiling supported in the next 6 months or a year from now, or do you have any details on the profiling side?
Well, for 6 months or a year, definitely. I don't have the exact details on each language because each one is its own working group, independently of the specification. I guess the main hurdle was to stabilize the data model. So that's once you have the data model, for those who are less familiar, then the implementation across the different SDKs is easier, or at least more technical. But the discussions about even deciding whether we go the pprof style modeling or something else, or that was the harder lift. But I think we've done that. So that's the major thing. But we need to check per programming like the working groups where it's going to stand in terms of implementation.
And I guess questions to you and Braydon, because Brandon, you're involved in the collector world. I guess in the collector will also have some updates once the profiling signal will be out there. So it means that probably we will do some processing on profiling, or this is something that not going to be part of the actual project.
Braydon, do you want to take it as a?
Yeah, I mean, I'm not an authoritative source, but generally the collector serves as something of a reference implementation at the same time as serving as an application for users to use. I have to imagine that upon the profiling spec, I mean, at least being in alpha or beta, probably based on patterns for previous signals, the collector in contrib will start to experiment with it and allow users to experiment with it. I don't think they'll like hold off until the spec is completely stable unless they're changing their strategy.
And maybe one more thing to say, the way that since it's been added as an independent signal, and by the way, it wasn't trivial. The beginning, the discussion was whether to even model it as a separate independent signal or to piggyback on existing facilitation of the spans or something like that. But the thing is that you have processing pipelines for the different signals. Obviously, you can cross and you can connect, you have connectors. So because it's a new signal, you'll have a whole pipeline support in the collector for processing, for collecting, ingesting profile data. So definitely the collector will have lots of activity there to facilitate profile pipelines. And also to correlate that with other signals. I don't know if you saw the release from Grafana about, so you already see discussions in the open source community about how to correlate profiles with other signals. So this is definitely something that the collector lends itself for these sorts of use cases. So you'll see processing designated for profile data, and you'll see starting to see correlations and connectors to with other signals. But I don't know to say when this will already be starting to take shape.
Yeah, I think from a use case perspective, I think it's clearly you have a trace, you have a span that is long. You want to understand this is where profiling comes in the picture. So having the profile connected to the actual trace, that will be so wonderful.
Yeah, that will be the next step in the drill down, definitely.
Yeah.
That's okay, but sorry, as someone who doesn't, I'm really not that in the weeds in the ecosystem here with OpenTelemetry. But can you do that? Like, can you really? Because there are technical challenges there. Like when you're looking at a profile, yeah, go ahead.
Yeah, so Periscope had that as a experimental feature before they were acquired by Grafana, where you were basically linking with OpenTelemetry. So it was like a wrapper in top of the hotel library, and the profile was getting the trace context when he was getting it. So you didn't have one profile for each individual trace. Of course, you had like a representative profilings, but I think it was very promising. At least I thought it was very useful. I mean, I was very excited when I saw it, to be honest.
Well, I want that as a former application developer. Like, I want that. Give me that. Like, that's the best thing I would get. But like, I'm just working through my head, like, how would I even implement that? Because like you have like you're profiling like every, I don't know, 100 milliseconds or every 10 milliseconds, right? And then like, I guess sometimes those happen to fall on traces.
Yep.
Like, there's interesting technical challenges. Also, Dotan, what you said about how to model it, and like you're doing the p-prof approach or something else. Like, where, if I can ask, like maybe it's too big to get into, but where are the trade-offs or like the considerations there in terms of how you model it even?
That's a big question. It was so many discussions. And by the way, bigger experts than me was involved. Folks from Pyroscope were there. The folks from
Polar Signal.
Sorry?
Polar Signals.
Polar Signal were there. The guys that were acquired by Elastic. I forgot their names. Really guys that are the top notch that I go to consult with them when I ask things about profiling. So they really got into the weeds of what's exactly the metadata that is there and the trade-offs. And also remember that the pragmatic approach, you have out there things. The question is whether you reinvent the wheel, you bring something entirely new, but then you faced with lots of end users migrating, or whether you align with something existing, even if it's not perfect, but it's 80% there, and then you have easier migration or compatibility with existing deployment. So, and then tooling and so on. So there's existing ecosystem for profiles. So lots of these discussions took place, and one thing about the model. So yeah, it's probabilistic, obviously, that you need to have the samples, but in a way you might think about it like exemplar. So like attaching the trace on the trace ID on the metric. So just conceptually, you may think about it as exemplars, or maybe the listeners of the show. This is how you could envision this sorts of thing going on.
Yeah. All right. So I'm looking at the time. So it's time is going very fast, to be honest. So I didn't see it. So I think we can. I can stay here for hours, but I think everyone has a own agenda. So thank you, first of all, Braydon, for taking the time and presenting. Thank you, Natan. It was a really good talk. Thanks, Dotan, for sharing the news on OpenTelemetry. I really liked it. And time to conclude. So I will let you say goodbye, and I will conclude this Observability Lightning Talk.
Thank you very much, everyone. And if anyone has questions that we didn't get to, or at least me, feel free to reach out to me at Horovits in any of the mediums, and happy to answer any questions. And I'll share the links with Henrik to follow up reading.
Same. If you have questions for me, reach out to Dotan. No, I'm kidding. Reach out to me. And great to see you all. Dotan, see you again, and Braydon, to meet you for the first time, and Henrik, you as well again. It's always a pleasure.
All right. Thanks, guys.
Have a good one.
Thank you.
All right. So thanks, everyone, for watching this live stream. A lot of great things that has been shared with an awesome panel. So if you enjoyed today's live stream, don't forget to like and subscribe. I will, for those who didn't have the chance to be connected today, the recording will be live. I will put some timestamps so it will be easier to navigate within the content. So thank you, everyone, to be here, and see you soon for another Observable Lightning Talks.